Okay, so good morning, everybody. I would like to start today with a small example of how to systematically solve a linear system. So we want to derive some kind of algorithm that will work always. So let's start with an example. Let's consider the following system. So let's write down 2x I'm going to use x1, x2, x3 instead of x, y, z. It's the same thing. So let me write it down first. Suppose we have this system here. x2 plus x1, x2, and x3 equals 5. Then we have 4, x1 minus 6, x2 equals minus 2. So I'm leaving gaps here where I have zeros, okay? Minus 2, x1 plus 7, x2 plus 2, x3 equals 9. Okay, so if you want, this can be summarized in the following form. In a very kind of concentrated way, you can write this as the matrix A times the column X equals column F. Okay, I'm going to use F for the right hand side. Many people use B because I want to reserve B, C, D, and E for other purposes, okay, which we shall see soon thereafter. So allow me to write F for the right hand side, because the right hand side means the given vector. So you want to solve for X, okay, so we're solving, this is the unknown, to be solved for notice that this is a square system. This is what we call a square system. So this is a square system, meaning that the matrix is square in the sense that the number of its rows equals the number of its columns. Okay, so it's basically Rn cross n, and in this case we have n equals 3. Okay, so this means that A belongs to this set here. Okay, remember this is the whenever we write Rn cross m, we mean a set of matrices with real coefficients and with n rows and n columns. Okay, so that's the dimension. So most of you will have probably already seen this kind of systems, possibly in high school or in some applications in the first year. And there's a widespread method which is quite systematic. It's called elimination. Okay, so elimination. This method. It's also known as Gaussian elimination, although it's it predates Gauss by many centuries, and it can be summarized in a 2x2 system. Okay, so let's write very quickly a kind of reminder of our 2x2 system, and then we see how it works. Okay, so suppose this is, so here I'm going to write x and y. It's just 2x2. Okay, so if I write x and y, so I don't have to plot out the board with subindices, and this is equal to say f and g. Okay, so this is like a miniature version of this one, and we'll see soon that this is not such a miniature version. Okay, and the key is will be to think blockwise. Okay, so first I'm going to work out the solution of this. Okay, and then we think about the blocks. So blockwise, block thinking. Means this. Means that you think of the coefficients of the matrix to be more general than just real coefficients, right? Anything that can multiply, in fact, works as a coefficient. Okay, anything that can multiply and that is distributive with respect to addition will work. Okay, so do you know any objects that are not scalars and that can multiply and are distributive with respect to addition? So my question is this: can we think of entities that multiply? Okay, so let's call them M. Mysterious objects, okay, that can multiply other mysterious objects, okay, so like N, P, and that behave this way. So usually multiplication is not indicated with any sign. Okay, so let's keep with that convention. It might actually give us a hint on finding operations where M, N, and P are not necessarily scalars. Of course, they could be scalars that already have the usual multiplication of scalars and the usual plussing of scalars, right? But what other objects can be plussed? Okay, let me change slides annotation to make it a little bit to hint more. I want to remind you. So what other objects can be plussed? Of course, vectors, right? So in vector spaces, that's why we introduce vector spaces. Okay, so anything that is a vector space admits this plus operation. Okay, so what are vector spaces that are not R that we know? Well, we already seen Rn, right? With n bigger than 1, strictly bigger than 1. Those are not scalars, they can be plussed. We've seen polynomials, okay, those can be also plussed. We've seen sequences, those can be also plussed, okay? Now, that's for n and p, right? Now, who is m? You can say, why don't you pick another vector, right? So you multiply vectors with vectors, okay? But when vectors with vectors don't return a vector, usually. Okay, there's something called the cross product that works in R3, okay? That's a very special operation that works only in R3, actually, which takes two vectors and returns a vector. Okay, that's the only product that does that. And actually, it's not such a easy to deal with product because it has many rules that do not work. Okay, for example, it doesn't have an identity. Okay, so you cannot get the same vector. Okay, whereas this type of operations would be really nice to have something which has the identity, and possibly that we can also undo the action of such thing. Okay. Identity and undo. Okay, so let's write down. So we want to have something like identity. Okay, let's call it 1. Okay, let's call it fat 1, right? To indicate that it's it's a special identity. But in fact, it's not that special. It's just the identity on the vector space. We would pick n and p, right? Well, I'm writing n plus p, but I could have written just n. Okay, so it doesn't matter. Okay. But the essential thing is this. Okay, so this is not necessary. It's a limit. Yeah. So the important thing is that 1 times n is equal to n. So we want to have 1. Okay, we want to have a 1. Okay, and also we want to have an undo. Okay, so we would like to have for an m, maybe not always, okay, but in most cases we would like to have something which kind of does the opposite of what m does. Okay, so we would like to have well, let's give it its name. Okay, it's usually when something does the opposite of something else in algebra, we indicate it with a superscript m-1, right? So this somehow refers to somehow this operation of applying, because we never write anything for that operation, the product here. Yeah, we never write anything here. Okay, so we just write m-1, right? And m-1 times m must be actually equal to 1. See, here I'm just writing these mysterious objects. I'm just using them directly without even looking at their action. Okay, because I know that this is going to work for any n. Okay, for any n that I put here, this is going to work. Right? So what am I writing here? Does this ring a bell? These properties that I have an identity, and that every element is invertible. And also I would like to have another property, the following, is that if I apply, which I subconsciously used here, okay, actually that's such an obvious one that we forget about it, but it's actually not that trivial, not that obvious. We say obvious, but it's a bad word, right? So suppose you have two such mysterious entities and they act on one element like this. You want also to have the ability of first, so you want the L not to act on vectors only, but also to act on its kind of like siblings, okay, so entities of the same type, right? And then apply that to N. So what are these three properties? 1, 2, and 3. These are the defining properties of a group, remember? Now, the problem with this approach is that we cannot always find an inverse. Okay, in group terminology, this would be the inverse of N. Okay, sometimes you cannot. There are certain in algebra you find out structures like this. Okay, but they just barely fail to be a group. Okay, because some of their elements are not invertible. An example is R. Okay, R itself. So are all the elements of R invertible with respect to the product? No, there's one of them which is not invertible, and that is 0. Okay? Okay, you can say infinity and start doing things with infinity and say that infinity is inverse. That's a bit of a wishy-washy, okay? Because it can be, it's useful, okay, and you can do lots of analysis with that, in fact. But the rules of algebra break down, okay, and then it becomes a mess. And the thing is that it's a bit arbitrary. So infinity times 0 is not always equal to 1. Sometimes it is 1, sometimes it's something else, depending on the interpretation that you give to infinity. Okay, whereas 0 doesn't need to be interpreted. 0 is 0, and we always know how it works. Okay, whereas infinity is not a single meaning entity. Okay, it has many meanings. Okay, so that's why we refuse to put it in R, and also it actually does destroy lots of nice properties. Okay, so no infinity. But in R, including infinity, which actually we didn't even need to start with, okay, just pointed out this because many people are tempted to write 0 times infinity or 1, and they think they're going to solve lots of problems like that. It doesn't solve problems. Okay, so in algebra, we just ignore infinity. And R is an example of places where we could take coefficients. And in fact, that's what we've been doing all our lives. Okay, we've been taking coefficients in R. But there's other places we can take coefficients. Okay? We can take them in C, for example. Okay, complex numbers. I haven't seen complex numbers yet, but as you know, you might take them there. But we can also go beyond that. We can go beyond complex numbers. Where can you find entities that multiply and satisfy these rules? Well, think of matrices. Right? Matrices actually do that. Not only matrices. Functions do this. Functions. Okay, so take functions that go from one set into another set. Sorry, not into another set, into the same set. Okay, so x is some generic set. Okay, and you take all functions that go from x to x. Okay, so you take the set of all f such that f is a function that goes from x to x. Okay, this is just another way of writing this guy here. Okay, so x to the power x. Okay, I explained yesterday why x to the power x means the function that goes from x to x. Okay, because essentially we can index all the elements here with elements from here. Okay, that's basically what f is doing, right? All right. This set here satisfies all these properties, right? It is associative, right? So with respect to composition, okay. So composition means that you apply and then you apply again. Yeah. We mathematicians write from left to right. Sorry, from right to left when we're composing. Okay, we start from the right and we go backwards. Okay, that's because of tradition. Okay, because we write functions like this. Okay? In fact, the function is written like this when this is meant to signify this. Okay, so if this is if y is equal to f of x is in fact it's x goes to y. Yeah? So x comes first and then f applies to it. And then goes to y. But the notation, traditional notation is f of x. Okay, so we're used to that. Okay, we're not going to change it, right? We just get on with it, okay? And we apply first the last, okay? All right, doesn't matter. The important thing is that if you apply first m and then you apply l, it's like applying l times m. Okay? I'm saying times because I like to think of the operation in my entity to be like some kind of multiplication, okay? Because it behaves like multiplication. Does this work in this set? Well, not for all. Well, let's start with first thing first. Okay, so associativity can be shown that composition is associative. Okay, actually, it's associative even if you don't stay within the same set. Okay, if you go from x to y and from y to z, it's the same thing as going from x to z directly. Okay, so associativity is quite a general feature for maps. Okay, identity. Of course, you have to stay from x into x. Okay, because identity is the map that for x returns x. Okay, it's the neutral element here. Okay. Some maps are invertible, some maps are not. Okay? Remember, those that are invertible are the bijective maps. Okay? Now, the bijective maps are maps that are injective and surjective, right? And it turns out that injective maps can be characterized as those who have an inverse only on one side. Yeah? So they're one-sided inverse. Yeah? So the injective is the one that goes and comes back. So it has a post-inverse. Okay, so it can be inverted after. Yeah. Whereas the surjective map is the other way around. It can be inverted before. Okay. So it turns out that these definitions, which look like quite different between surjective and injective, actually are dual one from another. Okay, from this algebraic point of view. Okay. This is just to say that all these concepts will come up when studying matrices. Okay? But what I really want to point out here is that what you need when you're doing this kind of matrix vector product, you don't need to have real numbers here. Of course, it works wonderfully for real numbers, okay? But these guys here can be any entities coming from such a structure. Okay? So those structures are known as algebras. Okay? So we talk about the algebra of functions. Okay? Because they have all the rules of algebra somehow in them. Yeah? Okay? So if you're part of an algebra, then you can do these things. Okay? There's more rules in an algebra. Okay? That's actually a group of transformations. Okay? An algebra is basically when you can also add and scale those entities. Okay? So as soon as X is a vector space, as soon as this X is a vector space, this becomes an algebra, which means that it has a subset which is a group. Okay, that's the subset of all invertible elements of such a set here. Right? And also, you can add functions and you can scale them for some field of scalars, which is usually the real numbers or the complex numbers. Okay? Why can you do that? Because as soon as X is a vector space, it allows you to do this. Okay? So for each X, you can, of course, sum these because these are elements of the vector space. Okay? And therefore, this allows you to define from some given functions, f and g, allows you to define a new function, call it f plus g. Okay, so in a programmer's terminology, basically the functions here are inheriting the structure that is given by the target set x. Okay, and same thing for scaling, right? So any operation that works in x will work on a set of functions that return values in x. Okay. So you end up having something which is an algebra. Okay, it's just an abstract version of matrices. Okay, so if you want to have a more concrete view of things, just think of matrices. Okay. Now, not all matrices are invertible. Okay, some of them are, some of them are not. We're going to see that. In fact, Gaussian elimination is exactly about that. It's to understand somehow which matrices are invertible and which ones are not. Okay, that's what the elimination of the day. Okay. So, but coming back to that, it's also this thinking in terms of algebras and coefficients and general numbers allows me to break down what I'm going to do next. Okay, so it will allow me to do the following. In this instance, what I'm going to do is I'm going to think of D. This D, I'm going to replace it with a capital D. I'm going to put a small cap on it. It's just, this is my notation, okay? And I'm going to underline it, okay? That's again my notation. So this means it's a matrix, okay? This I'm going to keep as a scalar. Of course, I could have taken also this to be as a matrix, okay? So I could have like two blocks. These are the so-called blocks that we call it. So when you say blockwise notation, means that you're subdividing your matrix into entities that are themselves matrices. Okay, that's the block thinking. Okay, but in this case, I'm going to take this one here to be quite small. Okay? It's going to be 1 by 1. Okay, so this one is going to be 1. So I'm going to indicate the number of columns like this and the number of rows like this. Okay, as if I was measuring the length of it. Okay, of course that's a bit silly. Okay, but it's kind of like good visual. And here I do n minus 1, where n is the dimension that I started from. Okay, in this case it would be 3. Okay, and of course I have to underline this, because if you think about it, this is n minus 1 rows and 1 column, where n could be bigger than 2, and therefore it is a column. Okay, it's a small column, so I put a hat in it. So for me, hat means small. Small means n minus 1. Large means n. Okay, it's just 1. Okay, that's terminology. Quick. Okay, so now if this is a column, what is this going to be? how much do I have? So D is n by, so the whole thing has to be n by n, right? So this whole thing is n, and here I have also n. So how much do I have here? I have n minus 1. So how much is D? D is n minus 1 by n minus 1. And how much is B? B is 1 by n minus 1. See how much to mean how many columns and entries, etc. Okay, so this is a column. I usually indicate, sorry, this is a row. Okay, I usually indicate rows with a capital letter. Okay? If it's a row of scalars, I don't underline it. If it's a row of vectors, then I underline it. Okay? Remember, matrices are rows of vectors or vectors of rows. Okay? Yeah. I always say vectors for columns. Okay, rows are also known as covectors. Okay, but many times we just say row. Okay, same thing here, right? So F and G, this should be a scalar, and this one here is a column. Right? How long is the column there? It's n minus 1. Okay? How about this one? That's 1. And that's n minus 1. Right? Let's check. Let's check if everything makes sense. Can we do a row column multiply here? Let's see. Scalar multiplies scalar. That's okay. Plus row multiplies column. What's the result of row times column? I'll remind you. You remember what we did some days ago? What is this? What does this return? Where star means just something, yeah? So it's just a quick way of writing something. Yeah? I don't want to mess around with numbers, just to remind you of the structure, yeah? So what does this return when you dot product of two vectors? Dot product is also known as scalar product. So it returns the product of the scalar product is a scalar, right? That's why we call it the scalar product. Okay, that's a good way to remember what the scalar product produces. Yeah, it produces a scalar. Okay, this is a scalar. In fact, I told you that dotting is essentially transforming this column into a row. Okay, so that's the result of dotting. Is basically transform this into. So whether I dot two vectors or I multiply a row with a vector, I'm going to obtain the same thing. And in fact, if you think about it, what we're doing here is multiply plus multiply, which is the same thing as you're doing here. Right? Of course, you should number the stars at this point. Okay? I'm not going to do that. Okay? So that's equal to the same scale. So let's come back here. What I'm doing is scalar times scalar. Okay, that gives me a scalar. And row times column gives me also a scalar, as long as the sizes match. Okay, does the size match here with the size here? It does. Consistent, beautiful. I like it. Okay, so this one here multiplied this one gives me this one here, which happens to be a scalar. Okay, so that's why block thinking is nice, because it allows you to reconcile everything at the end. Okay, the buzzer goes very quickly off if you do something wrong. You see it, right? So that's why I kind of like proselytize so much for it. Okay, so let's check this one here. What happens? Okay, so what is this? This is a column. Okay, I'm going to multiply it with a scalar. Column times scalar. What does it give me? Scalars don't change type. Yeah? They don't change the type of vector that I'm doing. Okay, so if I take a vector of size n minus 1 and multiply it with a scalar, I'm going to get a vector of size n minus 1, or a column. Okay. How about matrix n minus 1 by n minus 1 matrix times n minus 1 column? what is that going to give me? That's going to give me n minus 1 column. So I have n minus 1 column from the product of C with X, and n minus 1 column product of D of Y. What do I get? I get, again, 2 columns of size n minus 1. I sum them together, and the result is G. So the algebra is extremely nice. Okay? That's why we like to do blocks. Of course, the reason for doing blocks is not because we get nice algebra. Remember, algebra is just a tool. Okay? The reason why we do that is because this way we can break down the process of elimination into a single, let's say, task, which is solve the 2x2 system, and then reduce the problem to solving a subsystem here. Okay? So let's do the example first, okay? And then let's go through this in a more abstract way. Okay? So example. Right. So how can I do that? Okay, so let's start with the secret is all these x's here are just blurring our vision, okay? Because there's too many x's. Okay, so what we do is we get rid of them. Okay? I'm assuming here that you guys know how to solve the system, okay? If you don't, let's discuss it before I move to the matrix. So how would you solve the system here? Without thinking too much, just like by applying a rule. You would say, let me take the first equation here and subtract the product of it from the second equation. Okay? What is the product that we're going to multiply this one here to subtract from the second equation? You multiply by 2. You multiply this one by 2 in order to make this coefficient equal to this one here. Okay? So use the multiplier 2. Let's write it down here. Okay? So let's use 2 as a multiplier. Okay? And put this guy here. And then take the whole thing and subtract it from there. Right? Let me write it like this. Subtraction. Subtract this guy. Okay? So it's a minus sign, which tells you this guy. Okay? So the minus sign is a symmetric sign. Okay? That was a bad choice that they did like 500 years ago to indicate minus with a bar. Because the minus is not commutative, right? It should tell you who is minusing who, right? So this is a non-symmetric minus. Okay, so let's use it just today to indicate who I'm minusing. So I'm minusing this guy here from this guy. Okay. So basically, I multiply this one here. I'm going to get a 4, 2, 2. Okay, let me write down all this. Okay, so I'm going to write it down. Okay, so 2 is going to give me 4, 2, 2. Okay, so let me write it down. 4, 2, 2. And actually, it's also multiplying also the 5, right? Because I have to drag the 5. Just let me write it down. So that result there, which is going to be 4, 2, 2 here, I subtract it from this one here. Okay, I subtract it from this one. What do I obtain? So basically, I'm going to. Well, let me tell you the main point. The main point is I'm going to get a 0 here. I'm going to redo this again, anyway. Yeah. But I'm just going to draw attention that basically the scope of this operation is to make this 0. Okay, that's the goal of our operation. Okay, is to make this one here 0. And then you want to make this one here also 0 if you can. How would you do it? Well, now you can start afresh. You can take again the first equation, and you say take the right-hand side, the left-hand side, and I multiply it with 1 because I have minus 2 here. Actually, with minus 1, right? Because then I'm going to subtract minus 2 from minus 2 in order to get 0. Okay, so I multiply with minus 1. Again, same thing. Okay, so I multiply this guy with minus 1, and I subtract it from this whole. Of course, by doing that, I'm gonna also affect these values here, right? By doing this operation, I'm going to affect also these values, and I'm going to affect these values. Okay? Of course, I have to respect that. Okay? You cannot just change this one and forget about those. Okay? So I'm going to change that. So it's kind of worrisome. You're doing something, maybe you're undoing it on the other side. No, I'm being systematic. You see, because once I have all zeros here, I know that I can repeat this procedure on a smaller entity that remains here. Because what I'm going to get here is all zeros. It's as if there was nothing to do here. Right? This elimination procedure is going to make this one 0 and this one 0. Okay? So what I remain with is a smaller system in one unknown less, with one equation less. You see the block thinking? This is exactly what I'm doing here. Okay? So if I can solve this one for x, then I'm going to get another problem for y only. Aha, but the problem is smaller because it's n minus 1 dimension. So I got some progress here. That's a good step, right? Because I got rid of one dimension. And then I reduce it to a smaller one, and a smaller one, and a smaller one. So I have this cascade of problems that I'm solving by using the same procedure, because they all look the same. They all look like a square matrix multiply a vector equals another vector. Okay? This is Gaussian elimination. Alright, so now let's redo it again on the board in a way that will enlighten us, hopefully. Okay? So in order to be enlightened, we're going to use some colors, okay? Because these procedures can be quite messy, okay? And I'm going to try and do it in a way that is not too messy. In order to somehow remember what we're doing, I'm going to be using some colored chalk in order to... Okay, so my favorite colors are blue and orange. Okay, so I'm going to redo this from scratch. Okay. I'm going to repeat that procedure. At this point, you realize that these unknowns, they don't need to be dragged around. Okay, so let's minimize the amount of drag. Okay, this is like aeronautics. No drag. Well, we need drag. That's for another reason. Okay, so here we're not going to. Okay, so I'm just copying the system. And it's kind of like summarized way. Okay, but let me indicate each row with a different color. Okay, so I'm going to use orange for the second row, which is this one here. I don't waste chalk on zeros. Okay, so I just leave a blank space. All right. So that's the original system. Okay. All right. Now the first row stays the same. Okay. So there's no point in copying it. Okay. So I'm saving chalk. I'm not going to copy it. Of course, any reasonable person would copy it. Okay. So in a book, usually you see this being copied. Okay. So that's why I'm using color here, just to remind you which equation is equivalent to which. Okay. So, as we've seen there, what I'm going to do here, I'm just going to multiply this one with 2. Okay, so let me write the multipliers here. Okay, so the 2 multiplier is the one that goes for the second row. Okay, so I'm going to multiply with 2. And here I'm going to multiply with -1. Okay? And then I'm going to see the result. Okay, so let's do the result of the y1 multiplied by 2. Okay? what I'm going to get is 4, 2, 2, 10. Okay? Times table. Okay, I'm just doing a times table. This operation has a very fancy name. It's called a tensor product. Everybody gets tens. Okay, but in fact, it's quite simple, right? It's a multiply table. Okay. And here I'm just going to multiply the white with the blue, okay, to get something which I need to subtract from here. Okay, so let's multiply 2 by minus 1, and minus 2, minus 1, minus 1, minus 5. Okay, next step is to take the second guy and subtract it from the first, right? By matching the colors, okay? So let's match the colors. So this one here, subtract that, is going to be 0. This one, subtract that, is going to be minus 8. This one, subtracted from 0, is going to be minus 2. Okay? And this one, subtracted from minus 2, is going to be minus 12. Everybody okay? Okay. Now let's do this one here. Minus 2 becomes plus 2, subtract from there, 0. Of course, I have to get the zeros here, right? Because that's the whole point of this operation. Okay? These are the guys that make me, okay, a bit of silliness. Okay, just to remind you that this is the goal. That's why I write them, okay? Because usually I don't write zeros, okay? But this is, in this case, I just write them as a reality check. Am I getting 0? Yes. What do I have to do? I have to subtract this from this row, right? So now I have subtract minus 1 from 7, that gives me 8. And then I subtract minus 1 from 2, that gives me 3, right? And I subtract minus 5 from 9, which gives me 14. Okay? Good. Now, I do the same operation on this smaller system. But remember, the first row is already okay. I don't need to do anything on it. Yeah? So now I'm going to focus on this one here. So that's my new guy. Okay? So what I need to do is to kill off this guy here. Right? But I do it systematically. Okay, so I resist the temptation of writing the result, and I do again the same thing I did there. I have to come up with a blue multiplier. Okay, but let's do it more internally. Okay? So let's do it here. Okay? So the blue multiplier is going to be, which one is it going to be? It's going to be what you have to multiply this row with in order to subtract it and get 0. So I have to multiply with minus 1, right? Because if I multiply this with minus 1, I'm going to get exactly the same thing. So every time I'm trying to get the same guy. So here, in order to get the same guy, I have to multiply with minus 1. Okay? And I get minus 8, minus 3, minus 14. What? Sorry. Nah. See? I got it wrong. It's the orange guy that I multiply. Okay, so let's do something, okay? Let's remind ourselves, who am I multiplying by minus 1 and subtracting? Okay? So I'm multiplying the orange bar with minus 1. And then subtracting it from the blue in order to get the result. Okay, so the first thing is just multiply, okay? Because I broke it down in 2 steps. So there I did it in 1 step. Here I broke it down in 2 steps. Multiply first, okay? And then, so when you multiply here, I was multiplying the white guy. Okay, so this is multiplying the white guy, and this is multiplying the white guy by minus 1. Okay? So here we multiply the orange guy with minus 1, and what we get is a blue guy because I want to subtract the blue guy. Okay, so the colors are useful here because to see very quickly which equation you have to subtract from which. Okay, the very last step doesn't matter. Okay, but I'm just going to show this convention.
start with. Okay, so what I get here is -2 multiplied by -1. How much is that? That's 2. And I get -1 multiplies -12. And that's 12. So in order to finish off this elimination is I have to subtract.
Is it -8 or?
It's +8, right? Right? Because I have to be able to subtract this from this. Okay, so I was going too fast because I had -1 here is okay, and it actually gives me that. Yeah. So thank you, helping me. I'm dyslexic, and I need sometimes a bit of help with these things. Okay. And this is 0, right? And here I get 2 minus 2 subtracted from 3 gives me 1, and 12 subtracted from 14 gives me 2. As you already know, all these examples are concocted in such a way that the arithmetic is easy, okay? Because the point of this is not to do the calculation. We have computers, right? The purpose of this is to understand what is the procedure that the computer is doing when we're solving this. And this is exactly what computers do. They do Gaussian elimination. Not only, but that's the basis, that's the beginning of calculations with the computer. Okay? This is one of the fundamental algorithms in computing. Okay, good. So let's put things together now. Let's summarize what's going on. Okay, so let's take another board, copy. Word. Here. So the nice thing about today's lecture, I'm filming it, it's still going on, is that I don't need to take pictures because I'm making a movie. So that's great. Okay, so let's recap the information. So what we've got from the system is the following: is the first row is the same. Okay, so we get 2, 1, 1, 5. Okay. And you get this division here, right? And then we get all zeros, so I'm going to put a staircase. Right? So. And then the second equation, the orange equation, has been transformed into its final form, which is -8 minus 2 minus 12. And the final equation has been transformed into 1, 2. For a reason that's going to become very apparent, you should not ignore the transformers. Who are the transformers? The transformers are these multipliers that I had on the left. Those are very precious guys. So it's a good idea to keep them. And the magic of this Gaussian elimination is that it's so well designed that the space that you may be wasting for storing a matrix with lots of zeros is actually exactly the same size that you need to store those multipliers. So let me store them here, okay? With the staircase divide between the two, okay? So let's recap. So it's 2 minus 1 and minus 1. Okay, so this is everything I need. This information here, you guys are informaticians, okay? So the information that is here is exactly the same information that is there. There's no more, no less. But here it's more systematic because it allows me to solve the system very quickly. Not only this system, this allows me to solve all systems that have left-hand side given by that matrix. I'm going to show you in a second how that works, okay? But for now, let me solve the original system. Okay, so we're not done yet, okay, because we still have to solve this. Okay, let me use another color. I'm going to use red here. Okay, so let me Right, this is red. Okay, so what I want to solve is the white system, right? The red is just like some extra information that I put there on the side. I'm going to use later. Okay, but for as far as the solution of this system goes, I just need the right-hand side of this kind of. Okay, so usually we say that this is an upper triangle or an upper triangular matrix. Okay, so what I need from this calculation now is the upper triangle. Okay, so let's solve this upper triangular system. Okay, how do you solve an upper triangular system? You use this kind of backwards substitution that we did yesterday already. Okay, so that's known as back substitution. Okay, so back substitution. Yields the following result. Tell me that x3, how much is x3? It's equal to. Okay? How about x2? X2 is going to be minus 8x2, so I know this, I know minus 8x2, let me keep this, is equal to minus 12 plus 2 times x3, which I already solved for. So that's minus 12 plus 2 times 2, which is minus 8. Okay, because I used this one. That's why it's known as back substitution, okay? Because I work my way backwards in the system. It should be called upwards, okay? Because if we call this one back substitution, the upper triangular matrix should not be upper triangular, but should be right triangular, okay? But it doesn't matter. Some people do call them right triangular, okay? So, so terminology is very mixed up here, okay? So back, forward, all this is relative. Okay, left, right, up, down. Okay, it depends on how you're written things. Okay, but in this kind of writing, we are going up, going backwards. Okay. And this yields x2 is equal. So let's put boxes around the solution. Okay, so what is x2? X2 is equal 1. So now I can solve a back solve for x1. Okay, so 2 times x1 is going to be equal to 5. You see, this is also an algorithm. In fact, back substitution is also an algorithm. And we're going to review both algorithms now that we've done them. Okay, so it's 5 minus x2 minus x3. Right? And now I back substitute here. This is the substitution for x2, and this is substitution for x3, right? So that's going to be 5 minus 1 minus 2, which gives me 2. And here is the solution of our system. x1 is equal to 1. There's no need to fill the board with arrows, okay? Because anyway, they don't mean much, and everybody knows that we're deducing one equation from the next. Okay. All right. So this is basically the solution of the linear system. Of course, you are very precious people. Okay. You are very intelligent humans. The purpose of this is not for you to teach you this procedure. Okay. So don't try to cram this procedure in your mind. Just remember its purpose, and remember what it needs to do. That's why people like it, okay? Because it's easy to remember. All you need to do is to make those happy faces. Okay, and then to also store the information in a good way. Good. So this has solved the system. Let me come back to my initial observation. What is this for? Okay. So this is the magic of factorization. It's that I can, the original matrix that I had before is called A. can be written as the product of two matrices. The first one I'm going to call L, which comes from elimination and the shape of this matrix. Okay, the shape of this matrix is like an L, but that's an accident. The reason for the L there is because it's a lower triangular matrix. Okay, so there's a lower triangular matrix. This is not the whole of L. There's a bit that is missing. Okay, I'm going to come back to that. But it multiplies another matrix, which is an upper triangular matrix. Okay, and the reason why we like triangular matrices is because they are easy to solve. Not only that, we're going to see that they're easy to invert. Inverses. Okay, so inverses are exactly the type of things that I introduced at the beginning of the lecture. Okay, so after all, this procedure is designed in order to be able to invert matrices. Okay, that's basically what we're doing. Okay, so forget determinants and all that kind of stuff. Okay, that's not the right tool to invert matrices. The right tool to invert matrices is Gaussian elimination. Okay, one day we'll explain why this is a much better tool than Cramer's rule. Okay, so any one of you never heard of Cramer's rule? Never heard of Cramer's rule. Cramer's rule is the one they teach you in high school to solve linear systems by using the determinant. Who's never heard of the determinant of a matrix? Okay, that's very sad because I usually hope that people don't know what a determinant is, because you can do lots of linear algebra without ever mentioning determinants. Determinants are evil things. That's why we don't like them. They're evil from a numerical point of view. Of course, they're beautiful objects from a theoretical point of view, okay? And it's not true that I hate them. I love determinants. I actually use them in my own research, okay? But not for solving linear systems, okay? That's exactly, so it's a misuse of the determinant. To solve linear systems using the determinant is a misuse. It's an abuse. Not only abuse, it's really like, it's even worse than that. It's a crime. Don't do it, okay? That's it. Do Gaussian elimination. Gauss, yes. Okay, good. So let's understand what are these matrices L and U in this context. Well, it's very simple. You take L to be the identity matrix plus this little bit. So, reminder, what is the identity matrix? The identity matrix is, I'm going to write it in 3D here. Okay, I'm going to write it like this. Okay, so let me write it underneath this. Then I don't clutter the board with repetitions. Okay, it's already too many repetitions here. Okay, so the matrix L is going to be all zeros except on the diagonal I have ones. Okay, that's the identity. Okay, because if you multiply a vector with this matrix here, you get the same vector. That's the identity. That's the one I was talking about this morning. Okay, here it is. So this is the one of matrices. It's just a bunch of ones on the diagonal. Okay, everything else is zeros. Okay, so I don't have to denote them. Except in the L, you have to also take this red L-shaped array and you transplant it here. Okay, so that's basically 1. 2 minus 1 minus 1 is the multipliers that I was using in the Gaussian elimination procedure. Okay, and the upper triangular matrix is what's written there. So basically, this 1, 1, 1 is replacing the staircase that I've written there. And then I do 2, 1, 1. If you want to add that little silly thing, let's add it. Okay, it's just to see that. Okay, 0 minus 8 minus 2. 0, 0, 1. And then I do the 5 minus 5. Okay. Okay. So do I get A and do I get F? So basically what I'm claiming here is that this is Okay. Let's call this one V, column V. Okay. So what I'm claiming here is that not only A is equal to L times U, but also my little f there is equal to that. After all, this should not be surprising, okay? Because all what we're doing here, we're summarizing what we have done there, okay? Good. So let's see what's happened here. Let's check this. I'm not going to check the whole thing. Okay? I'm going to check 3 of them. Okay? If it works for 3, probably it will work for the rest. Okay? But of course, they shouldn't be the first 3. Okay? They should be somehow. So let me check for this one here. For this one here. For this one here. And for this one. Okay, so I'm going to recover. I would like to recover the original points. Okay, so by the way, here, subdividing like this. Okay, otherwise it will take us too much time. Yeah? So let's check this entry here in the program. Okay, so how do you do that? You take the first row here and you multiply it with the second column here. Right? So 1 times 1 and then zeros. Okay, so it's 1. That's correct. There was a 1. Okay? So I'm checking that my factorization, this is called also factorization because you're factoring a matrix into two factors. Yeah? Just as we were factoring numbers with prime numbers, remember last term? Okay? Here we're factoring matrices. Okay? So algebraically we're doing something very similar. Okay? Except here we're doing it for much more complicated objects than numbers. Okay, let's do this one here. This one times this one should give me this. Yeah? Let's do it. 2 times 2, and that's 0. Okay, so here I could have that's enough for this side. So just noisy. Yeah. So let me remove them. Okay, so it's just 4. Yeah. How about the last one then? That's this one here times this one. Okay, that's the longest one. It's always good to check. Okay, because that's somehow somewhere else. And you see how I did? I checked only in some kind of like. I'm making sure I'm covering all rows and all columns at some point. Yeah. You see that when I checkerboard? It's not a checkerboard. It's kind of like always exclude the ones I've done before in order to check that everything is correct. Okay? Because this way you kind of checksum all the rows and all the columns of your. Okay, so let's multiply this one here by this one. So we get -1 plus 2 plus 1. That's plus 2. Is that correct? Yes, that's plus 2. And then I'm going to do just one of the, for the vector, so I'm going to do the second one, okay, because that's the box there. So this guy here times the vector. So it's 2 times 5, which is 10 minus 12, and that's minus 2, which is correct. Yay. I hope this is still filming. Oh no. It stopped filming. It's still filming. It goes with a screensaver. It keeps on filming. I love computers. Okay. So let's stop here.